So what exactly is the Bohr model of the atom? Bohr was a scientist who was very much interested in knowing the changes of the atom and understanding the atom in detail. Just like we know, chemistry is mostly about the study of the changes that atoms undergo. So Bohr wanted to know what the atom behaves like, and hence devised the Bohr model. He says that in a hydrogen atom, the electron will move around circular orbits. The circular orbits revolve around the nucleus. So think about it as the way the earth revolves around the sun. So they are what he called orbits that revolve around the nucleus in increasing size. Now, further away from the nucleus, there are many circular orbits that we can't even count. Such, he said, there are infinite number of orbitals, or there are an infinite number of circular orbits around the nucleus in which electrons reside. So he proposed so because he knew that the nucleus was positively charged because of the protons that it contains, and the shells or the circular orbits are negatively charged because of the electron that it contains. And therefore, there's a force of attraction according to Coulomb's law, where we know that like charges repel and opposite charges attract each other. Here is a diagram that could help us understand this theorem more. Consider the atom. With the nucleus in the middle, we have the circular orbits beside. This is the nucleus, and these circular thingies are what he called circular orbits. So, where n is the principal quantum number, or what he called the value of the energy level, the ground state is n equals 1, which is the closest to the nucleus. In this state, the electron has its lowest possible energy, which we'll discuss later in the next videos. From n equals 1, the electron can make a shift to n equals 2 or to n equals 3 or to n equals 4, but this is highly dependent on the amount of energy that it will have absorbed. So say for example, you have eaten food that gives you some amount of energy. Now if that food is enough, you can move from where you are to the next point, and from there probably to the next point until the energy depletes, right? Now suppose the food you've eaten is not enough to take you to the third point, but it can take you to the second. So this is exactly what happens to electrons. Now sometimes electrons will lose energy, and when that happens, they move from higher energy states to lower energy states. They can move from n equals 3 to n equals 1, or from n equals 3 to n equals 2, and so on and so forth. So it is important for us to understand that when electrons move from a higher energy level, such as n equals 5 to n equals 1, they release energy in the form of light, or a photon. The letter n represents the energy level, which we will discuss more about in the quantum model of the atom, the quantum mechanical model of the atom, as being the principal quantum number. But as for now, let us just take n as representing the energy level, where the value of n increases away from the nucleus, and there are infinite number of energy levels. The shells get closer to each other as we move further away from the nucleus, and the value of n could be infinite, and at that point when the value of n is infinity, then the electron has zero energy. At this point, we consider the electron to be out of the atom completely. That is when it possesses zero energy. Therefore, all the values of energy for the electron inside the atom will be negative, because the most number that the electron can possess in terms of energy is 0 joules. Now here is an illustration, but instead of using circles, we've used lines. Notice that the lines are getting closer and closer to each other as we move further away. Suppose the nucleus is under the line n equals 1 here. The lines will get closer and closer to each other as we move further away. Now I'll make a video explaining the Lyman, Balmer, Paschen, Brackett, and Pfan series. But for now, all you need to understand is that as we move from the higher energy states in the above rows, when an electron moves from, say, from the 8th to the 1st energy level, we say it has entered the Lyman series. Okay, so any shift from upper energy levels to the 1st energy level is called the Lyman series of shifts, and you can follow that order from the 2nd to the 5th. Okay, now when it's at its ground state, an electron possesses negative 1312 kilojoules of energy, which can be converted into joules as 2.178 times 10 to the negative 18th joules. Energy levels possess energy, and as such, it's only common sense that the electron residing in that specific energy level will possess the same energy as the shell itself. Taking this constant known as the Rydberg constant, negative 2.178 times 10 to the negative 18th joule, it's actually the same as this one, except we multiplied by 1000 and divided by 6.022 times 10 to the 23rd. It's actually a conversion that I'll do for you in later videos. But right now, I just want you to understand the Bohr model, because it's important in understanding certain things about the atom. So the energy of an electron in a certain shell is given by this, according to Bohr's calculations, where in this case, n is the radius of the shell. Now remember, if we are talking about the first energy level, then n will be 1. If we are talking about the second energy level, n will be 2, and so on and so forth. Z is the effective nuclear charge, where, as we know, the nuclear charge depends on the number of protons. Therefore, for hydrogen, Z is equal to 1. So whenever we're talking about the Bohr model, Z will always be equal to 1, because the Bohr model was only as effective as to encompass the hydrogen atom, but not the other atoms. So we'll see that in later slides. Now we can modify the previous equation, by saying if an electron makes a shift from one energy level, say n initial, and goes into energy level final, which is nf, then the energy change of that electron, or the energy it emits or absorbs, is given by this equation, which makes things easier. Because say an electron moves from the 5th energy level to the 1st energy level, we know that it ought to have lost energy. Now, how much energy did it lose? All we do is simply put in ones where there are z's. From the 5th energy level, we say 5, and it moves from the 5th energy level to the 1st, so we put in 1 here, and we can do the calculations. It becomes quite easy. Here is an example. Calculate the energy required to excite the hydrogen electron from level n equals 1 to level n equals 2. Also, calculate the wavelength of light that must be absorbed by a hydrogen atom in its ground state to reach this excited state. Okay, so from the previous equation right here, this electron has been excited, or it has gained energy. To be excited simply refers to the gain of energy. So from its ground state n equals 1, we say this is the ground state because this is where the electron possesses its least amount of energy, which is a good thing. Too much energy in chemistry isn't good. Though it moves from n equals 1 to n equals 2, so we are going to calculate first of all the energy required to excite this hydrogen electron, this much. The change in energy is equal to, in this case, since the electron is gaining energy, we expect a positive value. But in a case where the electron is losing energy or emitting, we are going to observe negative values for delta E. It's a plug and chug thing. N final, since it goes into the second energy level, we put 2 here, and N initial is 1 since it moves from the first energy level. And then we said the nuclear charge for hydrogen is 1 because that's the number of protons in the nucleus, and doing the calculation you ought to find this value, 1.634 times 10 to the negative 18th, and it's a positive value because energy is being absorbed in order for the electron to increase in its energy level. And calculating the wavelength from the previous video in which I was explaining the photoelectric effect, we derived this equation. Now to find the wavelength, all we have to do is make lambda the subject of the formula, and then we can solve for lambda, which is the wavelength. Substituting Planck's constant and the speed of light divided by the energy value we just calculated, and here is the wavelength of radiation. Notice sometimes you have negative value for energy, but in this case, knowing that lambda can never be negative because length is a scalar quantity and not a vector quantity, then we can take the absolute value for energy every time regardless of the sign on the energy, whether emitted or absorbed. So the Bohr model turned out to apply to all other atoms, but it did not work. It applied to only the hydrogen atom, but it did not work for um, the other atoms. Say copper, sodium, it did not work for all others except for hydrogen. So it was very difficult to adapt to it. Although many scientists tried to justify it, but it did not work as expected. So electrons do not spin in circular orbits, and there's a newer model that we are currently using. It's not very new, but it was later than the Bohr model. So we'll come to understand it. It's called the quantum mechanical model, which is our next video. So if you happen to be watching this video, please stay in touch, and if you haven't subscribed to the channel, subscribe so that every time I post up a video, you get notified. We'll be talking about the quantum mechanical model, how to do electronic configurations, and all those things. However, the Bohr model is important. Although it was discarded, we still use it because it gave us some hints on very important phenomena. Okay, it proved that energy is quantized. Now, by quantized, before we conclude on this video, there is what we call emission spectra. I'll post a video about that because there is need for you to know about emission spectra. When a hydrogen atom releases energy and the energy is passed through a glass prism, it doesn't act the way visible light does, because visible light will produce a rainbow when it passes through a stream of water droplets. But the hydrogen atom will only produce certain lights and of certain colors, but not the whole spectrum. Okay, so in that case, we see that energy is quantized. Not all values of energy will be absorbed or emitted, but only specific wavelengths can be emitted by the hydrogen atom. So stay tuned for that video. It's actually coming up next. Thank you for watching. If you haven't subscribed, subscribe, like, and share. Have a great day.